Morning everyone. This is Sachin Kiste from Electrical Engineering Department, SND College of Engineering and Research Center. Today we are going to start one topic, that is quantization in electrical engineering related to sampling error. Okay. So before going to quantization, first all of you know that the basic commands regarding analog to digital conversion. A digital signal is basically a superior to an analog signal because it is more robust to noise and can easily be recovered, corrected, and amplified. And for this reason, the tendency today is to change an analog signal into digital data. And for this purpose only, the quantization technique can be applicable in case of control system engineering. In this section, we describe two techniques, that is pulse code modulation and delta modulation. Basically, the topic covered in this section is pulse code modulation, that is PCM, and DM, that is delta communication. So, moving towards the quantization system, first we have to need what is PCM technique. PCM consists of three steps to digitize an analog signal, that is sampling, quantization, and binary encoding. And before we sample, we have to filter the signal to limit the maximum frequency of the signal as it affects the sampling rate. Filtering should also ensure that we do not distort the signal, that is, remove high frequency component that affects the signal shift. In case of the sampling, this is a basic overview of the sampling system. That is, analog signal is sampled every t seconds, that is ts, and this ts is referred to as a sampling interval. Hence, f of s is equal to 1 upon ts, and it is called as sampling rate or sampling frequency. There are three sampling methods. First, ideal, second, natural, and third, flat top. So ideal means an impulse, and each sampling is performed at its instant level. Natural sampling will happen at a pulse of a short beat with varying amplitude, and flat off means sample and hold like a natural but with a sample or single amplitude value. The process is referred to as a pulse modulation, that is PA, pulse amplitude modulation, that is PAM, and the outcome is a signal with the analog value, that is non-integer value. See this diagram. This is a component of PCM encoder. So basically, sampling theorem, we need some blocks are given, that is sampling, then quantizing and encoding. Where an input is an analog signal, it is given to a sampling block, then it gets quantized and then encoded. So the analog signal have a basic value, but when it is encoded or when it is sampled, then it gives a digital data in the form of binary coding, that is 1010 or 0110, anything, but in the form of 1 and 0. So at the initial stage, when the analog data or analog signal is given to the PCM encoder very first samples it and it gives in the form of PAM signal, that is called amplitude signal. After that, it get quantizing and it gives the quantized signal. See this diagram, how this PM signal and quantized signal can be differ from each other. And after the process of PM signal get verified by the quantized signal, we get one value, and this value will be the digital data in the form of encoded system. Now, according to the Nyquist theorem, the sampling rate must be at least 2 times highest frequency contained in the signal. I am repeating again. According to the Nyquist plot or Nyquist theorem, the sampling rate must be at least 2 times highest frequency contained in the signal. One more point we are going to refer, this quantization converts continuously valued measure irradiance at the sample to the member of a discrete set of gray level or digital count. For example, the sample, that is f of x comma y, and example is f of 0, 0, means the value of x-axis and y-axis For PM or for amplitude, it is considered as 0, 0. Then it is equals to 1.234 or something like that, which is equals to or is converted to an integer in between 0 and some maximum value, that is 255 or whatever the value you have to be considered by an analog to digital converter or digital to analog converter. See here, a quantizer with m bit defines m is equals to 2 to the power m levels, and the most common quantizers have m is equals to 8 bit, means 1 byte. Okay, 1 byte is equals to, generally we considered it as a 8 byte, and such a system can specify 256 different gray levels, usually numbered from 0.255, where 0 is usually designed to black and 255 is considered for a white. Generally, image are digitized to 12 or even 16 bit. 16 bits means 2 bytes are becoming more common and have 4096 and 65536 levels respectively. Also, the resolution or step size, that is B, of the quantizer is the difference in the brightness between the adjacent gray levels, and it makes a little sense to quantize with a resolution B, and which is less than uncertainty in the gray level due to noise in the detector system. Thus, the effective member of the level is often less than the maximum possible value. The conversion from a continuous range to discrete level requires a thresholding operation, that is, for continuous range to discrete level requires a thresholding of operation and truncation, or it is rounding, and some range of the input brightness will map to a single output level. For example, all measured irradiance in between 0.76 to 0.77 might may to gray level 59, and threshold conversion is non-linear operation, that is, the threshold of the sum of two input is not necessary that the sum of the thresholds output, and the concept of linear operator will be discussed extensively, but we should say at this point that the non-linearity due to quantization makes it inappropriate to analyze the complete digital imaging system, and this is called as digitization or processor or display of the quantization system by common linear method. This problem is usually ignored as it appropriate for the large number of the quantized levels that are closely spaced so that the digitized image appears continuously. Thank you.